Good morning and good afternoon. Webinar is basically going to cover 5G and how it started in Release 15 and what we're seeing as we move on to Release 16, which is currently going on, and Release 17, which is coming up, what the features are, what the testing challenges is. Primarily, what I want to get out of this at the end is make sure that everybody on the call is able to have some sort of idea about first of all, the 5G landscape, what it looks like right now, what are the new features coming in, as well as what are the testing challenges. And again, there'll be questions answered at the end. Hopefully we'll have time for that. If there is no time, I'll be happy to take them offline. So without further ado, let's get started. So pretty much on the 5G side, the global 5G landscape, right? If you look at it right now, we've had about roughly about 381 operators who have launched so far in a total of 123 countries. So if you remember, the first 5G launch in North America happened in December of 2018. And in the first half of 2019, the remaining three operators has launched 5G. And shortly thereafter, we had launches in Korea, followed by in Europe, in Australia. So what we're seeing over here is that the 5G deployment is going on at a very fast pace. You can see over here, there are color-coded with respect to what the 5G launches have been, in what year and what they're forecasting in the future. So pretty much almost we have about, I would say 70 different commercial networks right now across 40 different countries, right? And when it comes to 381 operators, those are people who are running trials and seeing 5G evaluations to see what's coming in. So as you can see, pretty much launching started in December 2018. We're probably a year and a half after that, and we can see how widely that is penetrating, right? So moving on, that's on the network side on how the deployment is. If we look at the spectrum, like what is the spectrum that's being used, right? So what spectrum is primarily classified into low band, mid band, and high band spectrum, right? So low band is considered spectrum that is 1 gigahertz and below. Mid band will be 1 gigahertz all the way up to 7.125 gigahertz, and then above that, right now millimeter wave, you can go anywhere from 24.25 gigahertz to 52.6 gigahertz to be exact. So if you look at the overall market, if I focus mainly on the North American market, I would say the major deployment started on FR2, which is called frequency range 2 or millimeter wave. And there was here and there, a little bit of FR1 deployment, with respect to 600 megahertz, 2.5 gigahertz from some of the operators. But if you look at it worldwide, you can see that I would say majority and bulk of the deployment has been on FR1, right? FR2 is picking up. There are several reasons for that. One of them could be the fact that though that spectrum is not available in other parts of the world, it's a good thing it's available in the North American market, in the Japanese market, in the Korean market. We do have these millimeter wave deployment. But as you can see over here, on this chart, it's showing you the main band that has been there out for deployment has been the primary band, and the sweet spot we are at is somewhere between 2.5 to 3.5 gigahertz. That gives you the right amount of coverage, as well as it gives you the right amount of capacity and throughput that you can get out of those wider channels, right? So each of these different bands would probably have, the high band would have a different use case versus the mid band and the low band, and things that have moved forward, right? And as you know, there are more auctions happening. There was a recent auction that happened for 37, 39, and 47 gigahertz that just closed in March of this year. There was a 28 gigahertz auction that happened prior to that. So there's a 3.5 gigahertz auction that's being planned by FCC sometime mid of this year, right? So that's in works. So spectrum-wide, 5G caters to a lot more spectrum than what's being catered in 4G timeframe. Now, on the device side, what's interesting to note on the device side is what this is again taken from GSA editorial, and what it's primarily showing us on the left chart over here, showing us the growth of 5G devices, right? Starting in 2019, going all the way as of last month. So you can see that this is a steady growth starting from, these are the number of devices that have been announced, right? So, I mean, the number of devices announced can be, some of those devices are commercial devices, and some of those devices have not been commercialized, right? So altogether, there are about 280 devices as of mid of April that you can see, right? And the first announcements have started happening sometime in late 2017, early 2018, around the MWC timeframe. But there have been a lot of devices that have been announced. A lot of them have been commercialized. But the key thing to note over here when we compare this to 4G is the form factor, right? So the form factor is has a lot more variance than the form factor that we had in 4G. I mean, 4G, we had some CPEs, we had some IoT devices, and then, obviously we had the traditional handsets, laptops. But as we move on to 5G, it's opening doors to a lot more different use cases. So what we see in the the bottom left corner over here shows you the 5G devices by the form factors, right? So it shows that so far, out of the 280 devices that have been announced, about 38% of those devices are phones. And then right followed by that are CPEs, about 28%. And then you have modules, laptops. You will have, in the others category, which is about 7% right now, that is going to increase. You could have robots over there. You could have some sort of head-mounted displays. You could have AR, VR gateways. You could have vending machines. So the other factor is going to grow with time, right? And then from a frequency range perspective, as you can see, that the way the devices have been announced so far is pretty much the fact that it shows you what is the frequency ranges supported by these 280 devices. So as you can see, now these 280 devices can be some sort of a different form factor, but it could be different SKUs of the same kind of device that's targeting different regions. So keep that in mind, right? You could have a device working in meant for the Chinese market, but the same model may be meant for the US market, right? So the key thing to note over here is there are devices, the millimeter wave, the number of devices supporting FR2 it's certainly less than half of what have been announced to support FR1. But there are operators out there who are mandating FR2 support on their devices, and then there are operators who are supporting both FR1 and FR2, and some may have dominance towards FR1. So again, the key takeaway from this is the networks are expanding, 5G investment is continuing, the number of devices is, as you can see the chart, it's growing at a very, very steady. It's not asymptotic, it's going at a very steady rate over here. Alrighty, so moving on, if we go on into the 3GPP timeline, so if you look at where 5G all started, right? So 5G pretty much started with what we call phase 1, or which is release 15, right? So the work on release 15 in 3GPP, which is certainly a body that creates specifications. The work for release 15 started actually in June of 2016. And the work actually finished almost 3 years after that, in June of 2019 was the time frame when this finished pretty much. So what we can see over here is release 15, late 2017, it started. There was a freeze, which is the freeze of the basic protocol set, and then an ASN.1 freeze that happened sometime in end of Q1 around March of 2018. But the key thing to note is release 15 is the phase 1 has been pretty big. There are different network deployments. There is what we call the non-standalone mode, whereby you have an LTE anchor tied to the 5G NR, and then you have the standalone mode, which came later on, which we call option 2, and that got completed much later on, sometime in September of 2018 over here. And then there was work happening on other network deployment options, which I won't get into the details, but they were like option 5, option 4, option 7. Those were kind of pushed out, but there was a delay, roughly about 3 months over here. But again, phase 1 was completed, and the main thing over here, it was pretty much, when we look at these different stages over here, stage 1 is pretty much referring to your service description from the service user's endpoint of view, right? And then stage 2 is an abstract of the architecture of different function elements. And stage 3 is whereby, you know, you have your protocols that are going between different interfaces. So that's where the stages come into play. But the key thing to note is ASN.1 is when you have the protocol and all the pieces in place. Now these are the basic, these are the test specifications, these are more of the core specification that we're talking about, right? So again, phase 1 has been completed, and now we're getting into phase 2, right? So what is phase 2? So what this chart is showing you over here, we talked about release 15 getting completed in September of 2019, and now we're talking about release 16 and 17, right? So release 16 pretty much started, the work on release 16 started sometime, I would say, in September of 2019. You know, it was happening in parallel to release 15 work. And then there are different stages we talk about, right? So we have stage 2, stage 3, and then the ASN.1. Stage 3 is pretty much, you know, you have all your protocol stuff in place. Release 16 ASN.1 is whereby everything has been determined pretty much. And then RAN 4 that you're seeing over here, the RAN 4 is planned to be completed sometime in December of 2019, right? So, December of 2021. So basically what we're showing over here, RAN 4 pretty much is whereby you're looking at the different performances, right? That's what RAN 4 is going to be focusing on, the testing methodologies as well, right? So if you look at it, you know, release 16 stage 3 freeze, it got shifted by 3 months, right? So it's now normally this got shifted. This was supposed to be finishing sometime in March of 2020, but the release 16 stage 3 got delayed by 3 months. But however, the end date for ASN.1 freeze, that did not get delayed. But now there's an overlap between what's happening in stage 3 as well as ASN.1. So primarily June next month, we expect ASN.1 as well as the stage 3 to be completed, right? And again, as I said, stage 3 is whereby, you know, you make sure that the basic functionality and protocols, the interaction between the different interfaces or the physical elements are working fine, right? So that's the point. Now, RAN 4 is supposed to complete somewhere in December 2021. That's what the current timeline is, right? So that's, in a nutshell, what the timeline for release 16 is. On release 17 front, what's happening in release 17 is, okay, work has already started. The area we're in right now, the phase we're in right now, stage 1 is where we are defining the content of release 17. What is going to be in, there's going to be study items that are going on. There's going to be technical reports coming out of it. What we're looking at is what is the content definition. So we do have features in release 17, right? And as you can see, those pretty much December of 2019 was the time frame when the content definition got completed. So for release 17, we're kind of working more on the stage 2 part of it. And then the completion date that is currently targeted for release 17 ASN.1 freeze is December of 2021. So the stage 3 freeze, whereby your protocols freeze, your interface information is there, that is planned to be freezing in September of 2021, and ASN.1 freeze is going to be happening sometime in December of 2021. And then the physical layer stuff, which is what we call RAN 1, that freeze is going to be happening in June of 2021. So a lot of stuff coming in 2021. And then again, you have your RAN 4, which is your RF performance that is kind of targeted sometime in 2022. Again, now release 18, as I said, you know, the December 2019 was when we finished the content definition for release 17. December of 2021 of this year is when it's targeted to have the content definition for release 18. So this gives you a high-level overview of how the releases, you know, as you can see, completion, it's pretty much a year apart, maybe I would say about 15 months apart between release 16, release 17, release 17, and release 18, right? That's roughly anywhere from 12 months to 15 months. So that is the high-level picture with respect to how things are unfolding on 3GPP between release 15, 16, and 17. Okay, moving on, we're going to get into the different features, right? What are the different features, the verticals that we need to look at with respect to 3GPP. As you know, there were different features, or I would say there were limited number of features that were there in release 15. But as we move on, release 15 was primarily focusing on one thing, which was high throughput, extreme mobile broadband. LTE was also about high throughput. Release 15, the use case was extreme mobile broadband, high data rates, right? But as we move on into release 16 and release 17, we're trying to dividing these different basically use cases by different verticals, right? So the four main verticals, or I would say three main verticals we have are, one of them is industrial IoT, and then we have some other verticals which I'm going to talk about. Improvements happening on network deployment and automation. And last but not the least, we have what we call 5G device enhancement, right? So as you can see, pretty much release 16, was focusing on mainly on enhanced mobile broadband. But as we move on to release 17, there are incrementals happening, and we are working on better performances, better KPIs, better spectral efficiency that we can get. A lot of stuff that we were not able to accomplish in release 15 would be accomplished in release 16. Moving on. So this shows you a high-level overview of the different features that are coming in, and I'm going to go into some of these features that I think is important or are important. So from release 16 perspective, you have the new radio in unlicensed band. You have private networks. There is vehicle to communication. So CV2X is the other vertical I'm talking about. We'll dig in a little bit into the CV2X part, as well as on network deployment side, we have in network slicing phase 2. Phase 1 happens in release 15, not fully used because we don't have the 5G core completely implemented by the operators, but then there is this network slicing phase 2, and then device enhancement, right? We can't forget that, we have a device that is catering to so many different technologies, so many different complex antenna techniques. It's going to have a power drain on the battery, right? So what enhancement can we make? How can we make the devices more efficient? So those are some of the items in release 16. Release 17 will go one step further, right? And they will talk further, refine these different, feature set that can improve the security, the network service management, and the whole integrity of the 5G system, right? And you will look at things like NR Lite, which I'll talk about, side link enhancement, and then again, network slicing phase 3, and then other items like, enhanced MIMO, using, less complex NR Lite devices just for consumer IoT. So if key thing to note over here is in release 15, we started with only one use case, which is enhanced mobile broadband, but that use case has kind of basically transcended into 4 different areas, and those 4 different verticals are going to continue release 16 as well as release 17. All right, so moving on with respect to this, let's talk about some of these features. So one of the more important feature that I want to mention over here is what we call spectrum sharing and unlicensed band in 5G new radio. So if you remember, there were features in LTE like LAA, license assisted access, LTU, which was LTE unlicensed band using the unibands, and then we had ELAA, and there's so many of those features that really wanted to use this unlicensed band. Now, this is a great time to now use unlicensed band in 5G. 5G, the frame structure has changed from 4G. 5G has a lot of stuff built into it that makes it a lot more suitable than 4G. Things like having, shorter ACNAC time frame, right? That makes it easier of deploying unlicensed band, outdoors as well. So pretty much, this is going to be a release 16 feature. As you know, it's going to go anywhere from 5 gigahertz all the way to 7.125 gigahertz. That's unlicensed band to begin with. But then there is some work happening in release 17, which looks at how do we apply different waveforms and different multiple access techniques to higher frequencies that go higher than 52.6. So as you know, between 64 to 71 gigahertz, that's about 17 gigahertz of unlicensed band. Licenses, basically frequencies are very difficult to and more expensive to get, right? But we have 14 gigahertz of unlicensed band that's available between 64 to 71 gigahertz. So there'll be certainly use of that. I know 802.11ad has used licenses basically in around 60 gigahertz frequency range, but now this is a chance for us to use unlicensed band between 64 to 71 for cellular purposes. But again, for our purpose on this page, we're looking at mainly for NR unlicensed band in 5 gigahertz to 7.125 gigahertz. Again, it's going to vary because in some areas like Japan or Europe, they may have certain restrictions that are not there in other regions of the world. So mainly there's going to be some changes to the frame structure. We need to make sure that we can coexist properly with LTE. We can coexist properly with Wi-Fi. We implement listen before talk feature, which was there in LAA. But there are primarily going to be 5 different deployments that we're looking at right now. So scenario A is a deployment whereby you have carrier aggregation between a licensed band, which is going to be your primary NR cell, and an unlicensed band, which is your secondary cell or NR unlicensed, right? In this case, you could have your NRU secondary cell could have both downlink and uplink, or it could have downlink only as well. And then your primary cell is the one that's going to be connected to your 5G core. Now that's one example. Scenario B is going to be dual connectivity, right? So 5G, NR, NSA, it's all about dual connectivity, multiple different radio access technologies, communicating. So in this case, what's going to happen, you will have a licensed P cell, which could be LTE, right? And then you could have an R cell, which could be your S cell, right? So in this scenario, your LTE P cell is connected to your EPC, and then your P cell pretty much is connected to your 5G core network, right? So that's scenario B. And in scenario C, that is basically more of a greenfield situation, just like putting in Wi-Fi access points. You will have your NRU, and that's your new radio unlicensed. That radio will be connected to your 5G core directly. So it's just easy deployment. It's just like the way you have it with some sort of a Wi-Fi access point, right? So it's going to be directly competing with 802.11ad and 802.11ay. And then you have other scenarios like scenario D, which in this case you have a standalone NR cell in unlicensed band, right? And then you have uplink in licensed band. So your downlink is going to be unlicensed band, but your uplink is going to be an unlicensed band, right? And this scenario also you have your NR unlicensed base station is going to be connected to your 5G core. So 5G core is a requirement for that. And then you have scenario E. In this scenario E, you have dual connectivity between a licensed band as well as, and so you have an licensed NR band, and then you have an unlicensed NR band. And in this case, your P cell is connected to your 5G core network, right? So there's different deployment schemes that's being looked at, but this is again focusing on Release 16 for unlicensed band, which I think it's going to be a very important feature. Operators would have to jump on it for the fact that it's free spectrum, and nobody says no to free spectrum, right? So that's more on the unlicensed side. The other feature that I wanted to talk about that's going to be very important is what we called IAB, or it's called Integrated Access and Backhaul. So the function, the primary goal of IAB is to improve capacity. Improve capacity by supporting networks, with a high density of access points in areas, whereby you don't have fiber available, right? So again, fiber can be expensive to implement as well as maintain. And then you are also going to be able to improve the coverage by extending the range of wireless network, right? So it's not only having not having fiber in place, but also be able to extend. You can easily deploy these wireless node by providing coverage for isolated gaps, right? So you could have a UE in a building, or you can have an access point providing coverage to a UE with access point being connected, wirelessly to some. So you have the concept of a donor node, as well as you have a concept of an IAB node. So a donor node is pretty much the one that's going to be providing the main signal, right? And as you can see, you can have the donor node. Again, it's basically a separation of you have your CUs, which is your centralized unit, and your distributed unit, right? So in case of release 15, we had this concept of, the PDCP split. You had different ways of splitting. You could have your physical MAC layer on one in basically in your DU, and then you could have your RLC, PDCP, and higher layers in your CU. That way you can have a sort of a distributed network, right? So what we're doing over here is we are able to connect different nodes, different base stations or G node Bs together, right? So you can form a sort of a mesh network. And then eventually one of those nodes are, so the subsequent child node don't have to communicate with the core directly. They can communicate through a donor node that is being shown over here, right? But the UE can communicate with each of these nodes, can communicate with the child node, or it can communicate with the parent node as well. So that gives us a lot of flexibility of quicker deployment in high dense areas, pretty much, right? So there are different features we're looking at. This multi-hop backhauling, for FR1 as well as FR2. But the link between the nodes is primarily going to be millimeter wave link, FR2 link, because we need to have that high capacity, high bandwidth, but it's going to be over shorter distance, between the different nodes, right? But there are challenges. There has to be very much key synchronization across this whole topology. We should be able to operate, in sort of a dual connectivity mode with UE as well as IAB nodes. So it's challenging, but I think it's a very efficient way of using our spectrum, not only for the air interface between the UE and the G node B, but between G node Bs and G node Bs, similar to what we had the X2 interface. So we have the XN interface in case of 5G. All right, so this is more on integrated access and backhaul. Now we'll move on to the other vertical that we're talking about, which is IoT, right? So this is it's very important in the sense that URLLC, what stands for ultra reliable low latency communications, and how they're used in industrial IoT. So there have to be several changes that are pretty much made. In case of release 15, if you remember, the basic support for URLLC was introduced by having flexible slots, having different timing, different subcarrier spacing. As you have tighter requirements, you can have shorter latency in the order of half to 1 milliseconds. You can have 15 kilohertz subcarrier spacing all the way up to, for FR1, you can have 15, 30, or 60, and in case of FR2, you can have 60, 120 to 240. But as your subcarrier spacing increases, your TTI, your transmit time interval reduces, right? So you can send a lot of data in a much shorter time frame, right? And as you know, in 5G and our frame structure, we don't transmit per frame, but we're able to transmit on the order of the OFDM symbol, which is a big plus for 5G and our frame structure, right? So some of the items, that is going to be helping us with URLLC is, as I said, is the lower latency for supporting the different subcarrier spacing, shorter transmission time intervals. We have what we call mini slots, whereby you don't have to use all the 14 OFDM symbols, but you can group and transmit into a series of different less than 14 OFDM symbols, right? And then you can also do PDCCH monitoring, and then you can do a lot of something called what we call PDCP duplication, right? So there is going to be enhancement there, as we talked about different enhancements over here. So there's enhancement, on PDCCH, whereby we are able to configure different downlink control information, different sizes. So there are certain sizes that are used in case of 5G Release 15, but that has been increased. You can configure the DCI information for URLLC. That's a big plus. As well as you have some uplink share channel enhancement, right? Just like you have PDSCH, you had on the uplink side also there enhancement happening. We're supporting what we call cross slot boundary scheduling for both dynamic PUSCH grant and configured PUSCH grant, right? And then there's also talks about doing inter-UE prioritization that was shown over here. Basically, It's your uplink preemption by allowing the GNODB to interrupt data transmission, from one user to accommodate another user that has a higher priority data. So you can pretty much trigger which users are allowed to transmit data depending on what the priority of that specific transmission is, right? And then we have other items like, enhanced uplink grant-free transmission. That means you don't have to wait for grant. You can have sort of an asynchronous transmission. And then you could also have configured grant enhancements also, right? So pretty much 4 different areas, a lot on the physical layer side are going to make this URLLC and industrial IoT enhancements possible. Right, so moving on to other areas, if you look at is Cellular V2X, which was part of the other verticals, right? Cellular V2X is divided into 3 different phases. So we had what we call phase 1. Phase 1 was release 14, right? And release 14 was pretty much looking at, PC5 interface. It talked about the mode 4 operation that's defined by 5G AA. Pretty much there were very basic, safety use cases, with respect to what the requirements are. And again, it was mainly on release 14, right? So we had the devices would know there is some sort of provide any kind of collision warning. Pretty much that's what was pretty much on in phase 1 part. And then when we came to phase 2, in release 15, that introduced a number of new features in SideLink, like carrier aggregation, high modulation, latency reduction. So all these enhanced features in 3GPP V2X phase 2 were based on LTE. That was and then required coexistence with release 14 UE, in the same kind of resource pool. So I don't expect release 15, basically V2X to be very widely deployed. I think the big pick for release for V2X is going to be in phase 3, and then there is concept of as you can see in phase 2, the features were primarily based on high throughput, EMBB. There was nothing really specific to V2X, whereby you're actually using the SideLink, right, which is your PC5 interface. So what release 16 is doing right now is introducing NR V2X features using SideLink and also using the low latency functions, that we talked about for, industrial IoT. So it's kind of interconnected over here, if I may say so. And what the key thing that you will be looking at over here is the different areas that we're looking at. You have areas of vehicles platooning. This is mainly enabling devices or vehicles to dynamically form a group traveling together. So all the cars or all the vehicles in that group would receive the data from a leading vehicle, right? It's sort of similar to what I talked about IAB, but you have one group and you have multiple vehicles in it and one vehicle providing information to all the other vehicles. And then you have extended sensors, which enables the exchange of raw or processed data gathered through local sensors. And then we have advanced driving, which helps with semi-automated, or fully automated driving. You could have a longer distance between the vehicles as well. And then last but not the least is what we have the remote driving, right, which is truly autonomous. You have a remote driver, you have some sort of a V2X application that's going to, remotely control that vehicle. So those are the 3 different phases of Cellular V2X. As I said, we saw some items in release 14. I don't expect release 15 specifically for SideLink purpose to take popularity. But I think the dominance is going to be coming for features that are being deployed in release 16 for 5G NR-based V2X. All right. Now, the other item that we'd like to talk about is what we call satellite services, right? So 5G V2X, again, this is a release 17 feature. Satellite access, as we move from 5G V2X, which was release 16, now onto release 17, which is satellite access in 5G, right? So the objective over here is there are different use cases that I've mentioned over here, like roaming between terrestrial networks, and satellite networks and Internet of Things, and so on and so forth, right? So the key idea over here is what we're seeing is the device, you could have a device, and that device would be able to communicate, can form a sort of a relay. And when it forms a relay, it's able to communicate with other devices. So you can have device-to-device communication. So you could have one device that will be talking to a satellite, have satellite access, but that device would also be acting as a node that it can distribute services to other devices in that geographical area. So there are different ways of looking at it. You could have a sort of a ship, for instance, that is traveling. It's on land, and all of a sudden from land it goes onto the sea, but it still has to talk to the core network. So your satellite link would be communicating with the core network, right? So there are challenges over here. Obviously, you want to minimize the latency between your device that is communicating directly with your satellite services. So that's an area that we need to look at. Is it's going to be picking up in release 17 as we take a look at it. And then other items that we will be looking at is primarily, what sort of changes in architecture are going to be present, for this sort of non-terrestrial network. You can look at the feeder link here, or which is a backhaul. It's terminating in some sort of a ground-based gateway that is connected to the 5G core. So that's more on the satellite. I don't see much happening. Maybe in the next 2 to 3 years. Again, it will have a very good deployment into disaster areas, also with public safety networks. All right, so let's move on to the next part on what we call NR Lite. So NR Lite, as you can see on top over here, is in LTE we had the concept of narrowband IoT, category M1, or what we call enhanced machine type communications. That's at the lower spectrum. There are less complex devices, very low throughput devices, high battery life, and very low cost and low data rates, right? So those were the key parameters. But if you look at the color coding over here, and then you have the other set of devices that are doing HCC with 2x2 MIMO for FR2. Those are really enhanced mobile broadband. And then you have some low latency devices also, but those are full NR. Now this NR Lite is going to be something in the middle. It's a sort of, you can look at it, it's sort of basically a mix, a balance between the low power wide area devices, which were in LTE, versus the full devices, right? So, and examples of these devices could be your wearables, smartwatches, health services, medical monitoring, which don't really require a lot of, throughput. They may require decent coverage, but very low cost, very high battery life. So this spider chart over here is showing you the different KPIs like latency, reliability, data rate, and tells you, like, if you take an example, the enhanced mobile broadband, which is green over here, that requires you to have, the requirement is to have very high throughput over here, obviously, somewhat low latency. But if you look at the gray portion in here, that is striking a balance across all of these KPIs. So we don't want to have really long battery life, but it should be somewhere in the middle. So it's somewhere in the middle between low power wide area IoT as well as what we call full new radio. All right, so that is more on the NR Lite side. Again, the requirements, there could be different requirements over here for NR Lite. And the main thing is going to be the device complexity. We want to have new device, lower cost, lower complexity device size, have a lower, smaller form factor, and deployment scenarios whereby it should be able to deploy both in FR1, FR2, FTD, and TDD, right? So those are some of the items. And then we have other additional features that I want to mention over here that are coming in that I haven't gone into details, but some of them are basically, supporting higher than 52.6 gigahertz frequency, right? As you know, to support those, we are going to need new waveforms. The current OFDM may not work. It may be introduction of new numerology, different subcarrier spacing, because there are a lot of propagation issues that are associated with high frequency transmission. Other items that are coming in are, mobility enhancement. How quickly can we do handovers in future between FR2 devices or FR1 and FR2 devices? Those are also going to be playing a key role. And then, we have enhanced DSS. DSS means dynamic spectrum sharing. That is a very, very important feature in release 15. Moving on to release 16, that's whereby operators don't have to wait for frequency to be reformed. Use LTE bands in the same location, both frequency and time domain with 5G NR. So enhancement happening to DSS is on the PDSCH, whereby they're looking at using some symbols in the past were reserved for LTE and could not be used for NR. So they're kind of go from 8 symbols they could use in the past to 10 symbols. So there are some changes happening here. NR positioning, going from meters accuracy to centimeter accuracy. MIMO enhancement, HUE power saving is mainly supporting, RRC inactive mode, which is a new mode that was added in 5G. So those kind of things are some other features which I don't have time to go into detail about that would be happening in release 16 and release 17. So moving on, now we have talked about 5G features, release 16, release 17 features starting from release 15. Now I'm going to talk a little bit about the testing challenges, right? So what are the challenges we have and what are the solutions for those challenges? So first of all, if you look at it, the devices of today have to be really, really complex. They have to support FR1, they have to support millimeter wave, they have to support different deployment options like NSA and SA, and supporting, on top of that, they will have to support different radio access technologies, right? LTE, 3G, a lot of places still has 2G, 4G, and 5G, those are there. Supporting different bandwidths, different subcarrier spacing, when supporting FR2 and FR1, you could have a whole different sort of implementation on your transceivers on what sort of techniques are you using. Are you using hybrid beamforming? Because you have to use some sort of beamforming for millimeter wave, so you can focus your energy and kind of offset the propagation loss. So again, Anritsu, what we're showing over here is the Anritsu 5G communication tester, which is MT8000, and it can be used as devices, chipsets, RF front ends. And again, it's one box tester that will do your RF testing, your protocol testing, as well as your application level testing. So those are some of the challenges. So we need to have a system, a test system that's able to cater to each of these changing in technologies. So we don't need to have a new system when it comes to release 17. You want to make sure that the system that's there, the call box that is being used, is scalable to go from release 15 to release 17 and beyond with limited hardware changes. Right. Other challenges that we see in 5G is new power classes, right? So traditionally we have been testing power class 3, which goes all the way up to 43 dBm as the maximum EIRP. But as we go into the different power classes, like power class 1, for instance, which is kind of mainly on CPEs, right? So those have a much higher throughput power requirement, right? As you can see, power class 1 across the different FR2 bands can go all the way to 55 dBm. That is roughly about 16 times more power that we're transmitting at versus a handset, which is power class 3. So again, it's important that the test equipment is able to handle these high power, be able to have that dynamic range in there, and also make sure that it's not, the high transmissions do not adversely impact any of the components. So again, we don't want to have separate hardware for testing PC power class 1 devices versus power class 3 devices. So those are some additional challenges. And then I wanted to bring you guys onto the concept of OTA testing, near field versus far field, right? So as we go into millimeter wave, it becomes necessary that we need to test over the air, because first of all, your antenna array is really, really tiny. You could have an 8x4 antenna, something on the order of 3 centimeters, and it may be difficult to connect a device to it. And even if you're able to connect a cable to the device, to that antenna port, the propagation loss will be too high to do any kind of good measurements, right? So OTA testing is important. Now, OTA testing is divided into near field and far field. And within near field, you have a reactive near field, as well as you have a radiative near field, right? So ideally, we want to test what we're seeing is measurement point C and measurement point D, which are called your measurement points in the far field area, and those are kind of dictated by the number of how far you are from the antenna aperture over here. So antenna aperture is what we call D, uppercase D, divided by the frequency. So as your frequency goes down, your distance becomes larger, but you got to make sure, you got to take into account that when you have larger distances, your surface area will become smaller at high frequencies, so you could pack a lot more antennas, so your D may become smaller with respect to that. So again, far field testing is important. And then the other part is what we call near field radiative testing, which is given by the formula, R is the distance from the antenna aperture to your measurement point, which is given by 0.62 root of d cube by lambda. So it's pretty much directly proportional to the frequency. And what I'm showing you down here are three different solutions that Anritsu has with respect to testing in the near field, whereby you have a shield box. Key thing is you're testing in the near field radiative region, not in the reactive region, because if you're testing in the reactive region, like measurement point A, you will have a lot of distortion. You cannot demodulate the signal properly. So ideally, we want to test in the far field area, and the far field can be indirect far field or it can be direct far field. So there are two solutions that we're showing here that cater to that. What you see on the right is a direct far field chamber. What we see in the center is a CATR indirect far field chamber, or what we call compact antenna test range. All right, so few of the items that I wanted to mention over here is the fact that there are one chamber doesn't fit everything, right? So it's important that the cost is a very important factor. We want to make sure that we are able to cater to the cost for our customers in general, right? So if you look at it from a 3GPP perspective, what we have here is an indirect far field CATR chamber, whereby you have a parabolic reflector, you have a feed antenna, it's going to send signals over here. Those are going to be spherical waves, and those become parallel waves that they get reflected from the CATR chamber. And that's one of the Anritsu chambers over here. So we have this can cater to your transceiver testing as well as your performance testing and your RRM testing, whereby your angle of arrival is equal to 1. That's one way. Now comes the point, now how do you test multiple angle of arrivals, right? So there is a solution, which is a very easy solution, is to do, I have a 3D impact chamber, which is a direct far field solution. So for RRM testing, the essence of RRM testing is to be able to test with at least 2 angle of arrivals, and the angle can be 30, 60, 90, 120, and 150 degrees, right? So simple solution, but very expensive and very costly solution is to have a 3D impact chamber. Now this is direct far field, so your far field distance is pretty high. The reason why we use indirect far field is to reduce the amount of far field distance. But this is going to be a very expensive solution. Plus, you have a customer would not want to use 2 different solutions. One for TRX performance testing, and other for RRM angle of arrival greater than 1, right? This is going to be a very expensive solution. Another solution, which is also expensive, is have a mixture of what we call indirect far field and indirect far field. So you have multiple CATR lenses, you have multiple CATR reflectors that you can see spaced out at different angles. Again, this is going to be not as big a solution as what we have in MPAC, but it's going to be fairly expensive because you're going to require to have multiple CATR reflectors over here. That's the other option. What Anritsu has, or what we have proposed, is to have one solution to be able to use the same CATR chamber we have for RRM angle of arrival greater than 1 testing as well. And how do we accomplish that? Accomplishing this is going to be a mixture of IFF, which is indirect far field that you see over here, as well as direct far field. So you can have some antennas on top which can move with time, so you can have that right angle with this parabolic reflector, and that way you can retrofit your existing CATR chamber to be able to do all the conformance testing, your TRX testing, your performance testing, your RRM testing for angle of arrival equal to 1, as well as angle of arrival equal to 2. So that's a challenge, and Anritsu is marching forward with it to meet that challenge, to have one sort of chamber for our conformance testing customers. All right. Other items that we have that we need to look at is what we call testing time. So testing time is a big problem. We need to reduce the amount of time it takes to test a device. And when we have FR2, that testing time does not become smaller, and the testing time keeps on increasing. And the reason for that is it's pretty much, you have to take measurements at different grid points, and you do a baseline beam peak search. So you normally try to search for the peak angle where you have the highest EIRP strength, effective isotropic radiated power, and then you lock your beam and do all your measurements. But to do that spherical scan, to find that, it takes a long time, and it all depends on how large your beam is, what your angle of the beam is as well, and and how fine it is. So the more the grid points, the longer it's going to take. So there's different ways implemented, and Anritsu has implemented, again taken from specifications, on how to reduce the test times. And one way is what we call coarse and fine scan. So what we can see over here is we try to determine initially where the high beam peak is, right? So if you look at the blue, purple, and magenta colors, it doesn't make sense to do a scan in an area whereby you have a very low signal strength, right? So you would want to focus, instead of doing entire sphere, you would want to focus in an area whereby it's you're more probable to have your peak search. So you do what we call core scans. Core scans are much more geographically dispersed. You don't do, and then once you have found that area, what you see on the right side is, okay, I have an area that certain phi and theta, I'm going to be getting my peak beam, and then you do fine scan between that. So you don't really have to measure all the points, and that reduces test time, right? The other part, what we can do is what we call constant step size and constant density. So constant step size is a way whereby your grid type, you have your measurement points that are evenly distributed on the surface of a sphere, right? So you can see it's changing by every 15 degrees. So you probably have about 266 different points over here. The other option is constant density, right? As I said, constant density is you have your measurement points that are evenly distributed on the surface. In constant step size, they are not evenly distributed, but they are at regular step intervals. So constant density would take less number of points, and you can save your spherical scan time, which is the bulk of the time it takes to do these frequency range 2 tests, right? So that's another thing implemented. So key takeaways, 2 methods of doing it. There are a lot of patented methods that we have introduced, but high level, which is available in the specifications in 38.810, are coarse and fine scan and constant step size and constant density. Last but not the least, just wanted to give you guys an overview of the different areas of 5G. Anritsu has been engaged in 5G for over 3.5 years, I would say, right now, and we play a key role in different phases of testing, going from component testing all the way up to production testing, going through chipset R&D with the chipset vendors, as well as doing certification testing. So the key item is the MT8000, which is our network emulator for 5G. It's reused in all of these different components over here. That's the kind of the brain of our test systems. So that being said, I would say, in summary, we talked about the spectrum utilization and the landscape, and then we talked about the evolution of 5G features, going from Release 15 to Release 17, and some of the test challenges and solutions. So again, it's a lot of stuff in an hour, but or I would say less than an hour. But I would certainly welcome any questions. And as I said, if we can answer any questions due to the time constraint, I'll be happy to take them offline. My email address is right below there. And you can certainly feel free to send me an email with any sort of question. I'll try my best to respond back. Again, thanks very much for your patience and your time and your dedication.
Thank you very much, Adnan. I do have a couple questions that we have time for. So the first one is kind of lengthy, is regarding the test chamber. It is my understanding you need to calibrate the device in the chamber to get accurate measurement. The question is, just one position for different bands? Also, how often do you need to adjust? Weekly, monthly, or yearly?
Good question. So basically, the calibration for these is done on an annual basis, and there is 3GPP defines how calibration portion, as well as how the quiet zone, as we talked about different frequencies, right? So the chamber has to be characterized across different frequencies, and 3GPP specification 38.810 defines exactly, at how many different, so basically we take an antenna at different angles of phi and theta. We take it at 7 different points, and we go around 5 different phi and 5 different thetas at different frequency ranges. And we need to correct, the main thing is to characterize the quiet zone. You want to make sure we're getting the right quiet zone, and that the amplitude and phase are within a certain amount of measurement uncertainty in that specific quiet zone. So again, it's done on a yearly basis. It's the characterization, but the calibration is on the yearly basis. Characterization happens once, and after that you have what we call the calibration again on an annual basis.